Okay, recording's live. Animation is set. Okay, so a little bit quicker lesson this time around. We'll be talking about tangent lines, normal lines, and Euler's methods. So before I get into different types of linear approximations that we'll be doing today, I want to go back and talk about forms of the equation of a line really quick. So there's a common theme I've seen in the past couple years where almost everyone wants to give me the equation of a line in slope-intercept form. But a lot of times it's faster to give it to me in point-slope form, depending on what information you're given in a problem. So a lot of times on your AP exam, because we're so time crunched, I'm going to be using point-slope form a lot whenever we need the equation of a line, just because the information that we're given is quite often just a point and a slope, since we'll be getting the derivative with our slopes. So you see that crop up? That's why. Point slope form is the change in y is equal to our slope times change in x. Which makes sense if I rewrite this. Change in y is equal to m times change in x. If I solve for m right now, then I would say my slope is equal to my change in y divided by my change in x. So the first thing we're going to look at is an equation of a line that's tangent to a curve. Because our derivative a derivative is the slope of a function at a point. Which also means it's the slope of a tangent line to the function at that point. A tangent line is a line that only touches our function at one point. So if I was going to draw a line with the same slope that our function has at this point at x equals 1, and we can do that by deriving our equation. So in this case, our function is x cubed. So if f of x is x cubed, then our derivative would be 3x squared, and my derivative at the point x equals 1 would be 3 times 1 squared, or 3. So in that case, I know the slope of my line is 3, and I know my point on this function is at 1, 1. So with that information in point slope form, I could do y minus our y value, which is 1, is equal to my derivative at that point, which is 3, times x minus our x value, which is also 1. And I would get the slope of the line that is tangent to the function x cubed at the point x equals 1. Any questions on what we did here?
No.
Okay, let's try a couple more. So I've got a couple more functions here. I'm going to take a look at the first one first, starting with Andrew. I want to create an equation of a line that is tangent to this function at the given point. What do I need to do first?
I would derive the equation y.
Okay, so I'm going to get general form for the derivatives. This is y prime is equal to, what happens when I derive?
Negative 4x plus 8.
Okay, then we need to take that general form and figure out what our derivative is at this point. Eric, at this point, how can I figure out what the derivative is? What do I need to plug in? Jump in here. Eric, can you hear me?
Yes.
Okay, for our derivative here, If I want to figure out what the derivative is at this point 3, 1, then what would I have to plug into our derivative?
3 and 1.
3 and 1, okay. I don't have any y values for my equation, just x values. So I'm going to plug in the 3. So our derivative when x is 3 would be negative 4 by 3 plus 8. So what's our derivative?
Plus 4.
Really close.
Oh, negative.
Negative 4, okay. So Kyle, we've got a point and we've got a slope. So what can we write for our equation of the line?
So y minus b, so that's y minus 1 is equal to negative 4 times x minus 3.
Perfect. I'm going to go ahead and write our general form above that just for everybody else. So this is our change in y, so that's y minus b is equal to our derivative. So that's the derivative of our function, in this case y prime, at our x value a times x minus a. Okay, so this is fine if they just ask for an equation of a line, but they asked specifically for us to write this in slope-intercept form. So Andrew, if I can keep going, how can I rewrite this into slope-intercept form?
First I would do for the right equation I'll use distribution method.
Okay.
Distribution stuff for like negative 4x plus 12.
Perfect.
And I will move negative 1 by adding 1 and eliminating 1 on the left and add 1 on the right. So it will be negative 4x plus 13.
Awesome. And now we're in slope-intercept form, so we should be good to go. Okay, I'm going to recap really quick for the people who just joined. Oh, okay, I guess it's Niall. So far, we are using point-slope form of a line. I'm going to figure out what the equation of a line that only touches our function at one point would be, which is what we call the line that is tangent to the curve. A tangent line would have this form in point-slope form. So that's y minus b is our y value for our point equals our derivative at a, which would be our slope at that point, times x minus a. Or in other words, change in y is equal to m times change in x. Therefore, slope is equal to dy over dx, which we know is true. So that does mean that a derivative is also the slope of a tangent line to the curve. Which we solved here. I'm going to do one more and start calling on people again. So starting with Eric. I want to find the equation of a line that's tangent to this curve, y equals negative sine x at 0, 0. What's the first thing we need to do?
It's not showing the problem.
Okay, so we're going to need to derive. What happens when I derive?
Negative cosine x.
Okay, Kyle, if I plug in 0 right now, what's going to happen?
0, if you plug in 0, it's going to be negative 1.
Okay, perfect. So I've got a slope and we've got a point. So I'm going to jump to Andrew. What would my equation be then?
it will be y equals -1 times x, so y equals -x.
Perfect. That's because A and B are 0. I'm going to go ahead and write my step just for everybody who's not here. So this is y minus 0 is equal to -1 times x minus 0, or y equals -x. Okay. Maya, you okay?
Yeah, I'm here.
Okay, cool. So I'm going to have you help with the next one. What's our first step if I want to find the equation of a line tangent to y equals e x minus 2 at 3e?
So first we derive.
Okay. What happens when I derive this?
Uh, is it's going to be just ex -2.
E raised to the
It's
x
not going
minus
to
2.
change.
It doesn't change at all, right? If we derive e to the u power, it'll become e to the u prime. But in this case, if I derive the power, if I derive x minus 2, I'd be multiplying by 1. So my function does not change in this case. Okay. And then I need to plug in our point. So when I plug in our point, what's going to happen?
It's going to be ex raised to +1.
E raised to the positive first power. Perfect. Okay. And we're jumping to, I think we're back to Andrew again. Andrew, what do I do with this?
I'll convert 3 to x, then it will be e, so I'll convert into the slope intercept form, and it will be y minus e equals e times parentheses x minus 3.
Okay, so this is point slope form right now. And then Eric, how can I transform this into slope intercept form?
Plus e to both sides.
I'm going to add e to both sides. I need to do one more thing as well.
Distribute.
Distribute. Okay, so let's go ahead and distribute first, and then we can add e to both sides. And what will we end up with?
Ex minus 3e plus e, so 2e, -2e.
Awesome. Ex minus 2e. Okay, and that's slope intercept form, so we can leave it right there. All right, last one. Kyle, what do I need to do first?
Derive.
Okay, I need to derive first. What's going to happen when we derive?
-1/3. Y prime is equal to -1/3 times 2x minus 4 power. It's the power of -2/3. times. Yeah, that's so two.
Times 2, perfect. Okay, I'm multiplying by 2 because of chain rule. I have to multiply with the derivative of the inside function. Everything looks good. So then, Niall, over to you. What do I need to plug in?
-2 and 2.
Okay, I don't have any y values, so what do we need to plug in?
Wait, isn't it -2?
Yes, -2. Our function only has an input of x values, so we just need the -2 from this point. If our equation did have a y in it, then I would also need to plug in -2 and 2, which I would subscript like this. It's still okay to subscript like this if you don't have a 2 for your y value. It's just a little bit weird because you don't have any 2's that you're actually substituting in. Okay, so I'm going to substitute this for my x value. That gives me -1/3 times 2 by -2 minus 4 to the -2/3 power times 2. Okay, I need to simplify this up a bit. What's the first thing you see that you would simplify?
First one. So we need to sort out was 2 times -2 minus 4.
Okay, what is that? Everything inside that parenthesis?
-8.
-8. Okay, so now I've got -1/3 times -8 to the -2/3 power so far, right? Times 2.
Yeah.
If I'm raising something to a negative power, what does that mean?
Wait, can you say it again?
If I raise a number to a negative power, what does that mean?
Raise the number to the negative power is going to be 1 over that number.
Perfect. So this is y prime -2 equals. I'm going to take this +2 and multiply it by the -1/3 to simplify the steps. This becomes -2/3. And then this number will be 1 over our number on the inside. So that's times -1/8. And now I'm raising this to the +2/3 power. So I'm going to write this like this, I think. Times 1 over -8 raised to the +2/3 power. Okay, if I'm raising something to the power of 2, I could square it. And then if I'm raising it to the power of 1/3, that means I could take the cubed root. So I'm going to take the cubed root first. What is the cubed root of -8? Might run out of space to do this on one line.
It's going to be square root of 64.
Okay, if you want to do it that way, then I'm going to square the -8 to become 64. So this is 64 raised to the 1/3 power. If I raise something to the 1/3 power, that's the same thing as taking the cubed root. So now I need one number that you can multiply by itself 3 times in order to get 64.
Oh, can you say it again? I'm sorry.
Yep. 64 to the 1/3 power is the same thing as the cubed root of 64. Cubed root of 64. So you're looking for one number that you can multiply by itself 3 times to get 64. Okay, if you're not sure, I've got cubed root of 64. I can rewrite 64 into factors. What numbers could I multiply by in order to get 64?
Our 4.
4, okay. So 4 cubed is 64, so therefore 64 to the 1/3 power is 4. Okay, and I can multiply straight across now, so this is -2 on top divided by 12 is -1/6. Okay, last step, over to Andrew next. Andrew,
Yes.
what's the last step?
It will be y minus 2 equals -1/6 times parentheses x plus 2.
Okay. And we are supposed to write our answers in slope-intercept form, so I need to simplify a bit.
So it will be y equals -1/6 x plus 3/4. I mean 4/3.
Okay, I'm gonna write that out. So this is minus 1/3 plus 2. Right, so
Yes.
that 2 is 6/3. This is 6/3 minus 1/3 is how much?
5/3.
5/3, there we go. This 1/6x plus 5/3. Okay. Any questions on any of these? Cool, we're looking good. So I'm going to show you what this might look like in a free response. This time I'll work through. So I've got an implicit function, so that means we've got both x and y's before we go to derive. Xy squared minus x cubed y is equal to 6. The first thing they want us to do is to prove that our derivative is equal to this. So I'm going to go ahead and derive. If I derive xy squared, this first part here is product rule. So when I derive the x, I get 1, so that's 1y squared plus, when I derive the y squared, I get 2y to the first power times the derivative of y. So that would be 2y dy over dx times the x I had originally. Is everyone okay with this part? Okay, I'm deriving in terms of x, so the reason why I wrote 1 here instead of a dx is because if I'm deriving in terms of x, I could have written a dx over dx for that point, but dx divided by dx is 1. It will cancel out. So I don't need to write it. Okay, so that first part's product rule. The second part, also product rule. I've got negative x cubed times y. So if I derive that, it will be negative 3x squared y. Again, with chain rule, that would be times dx over dx, which is 1, and you don't need to write it. Plus negative x cubed times the derivative of y, which would be dy over dx. Equals, if I derive 6, I get 0. Okay, is everyone okay with this part as well? Also product rule.
Yes.
Okay. So from there, my goal is to solve for dy over dx. So I'm going to move every term that does not have a dy over dx to the opposite side. So that means this negative 3x squared y, I'm going to add to both sides. So that moves to the right side. And this y squared, I'm going to subtract from both sides to get this negative y squared. Okay, now every term that has a dy over dx is on the left side, and that will allow me to factor it out. So this is the opposite of distribution. I'm going to pull out my dy over dx from both of these terms. And that allows me to divide both sides by everything that's not dy over dx to get my answer. So if I divide both sides by 2xy minus x cubed, I'll get my derivative of y in terms of x. Any questions on part A?
No.
Okay, looking good. For part B, I want to find all points on the curve whose x-coordinate is 1, and then write an equation for the tangent line to each of these points. So the first thing I'm going to do, I want to find the points where the x-coordinate is 1, so I'm going to plug in x equals 1 and figure out what my points are, so what are my y values there. So I'm going to go back to my original problem here, xy squared minus x cubed y equals 6, and plug in 1 for x. If I do, I've got y squared minus y minus 6 equals 0. Which does factor into y minus 3 and y plus 2. So therefore, I've got y equals 3 or negative 2. So we've got 2 points, 1, negative 2, and 1, 3 for this curve where our x-coordinate is 1. And they want us to write an equation of a tangent line for both of these points. Okay, so I'm going to take my derivative. Which we had here, and plug in the x and y values for each of these points, starting with 1, negative 2. Okay, so that's starting with 1, negative 2. Plug in our x and y, and I get negative 10 over negative 5, which is the same as 2. So if my slope at 1, negative 2 is 2, and my point is 1, negative 2, then we can plug that into our tangent line equation for y minus b, that's y minus negative 2 is y plus 2, equals our slope, that's our derivative at the point, which is 2, times x minus a, which is 1. And I've got the equation of a tangent line. But this time they did not ask us to write it in slope-intercept form, so it's okay to leave it in this point-slope form, since that's still a formal equation of a line. So if they don't ask, then give it in whatever form is easiest to write it in. It takes the least amount of steps to write it in. Any questions on the first point? Okay, same thing for the second point. We said when x is 1, y could also be 3. So if x is 1 and y is 3, I can go into our derivative and plug in 1, 3. So that gives me 3 times 1 squared times 3 minus 3 squared over 2, 1, 3 minus 1 cubed. If I plug all of that in, I've got 9 minus 9 on top, and I've got 6 minus 1 on bottom is 0, so I've got my derivative is 0. If I plug that into our point slope form, all of this right side is going to be 0, which means y is 3. Okay, any questions on B?
No.
Last one, part C. I want to find the x-coordinate of every point where the tangent line is vertical. If our tangent line is vertical, then that means my line would go straight up and down. And if I have a line that goes straight up and down, then that means we do have rise, but we have no run. Which means our run will be 0. So as long as you've got a vertical line, our slope is something over 0. So I'm going to set the denominator of this slope equal to 0, and we'll solve for our x and y parts. So if I do, 2xy minus x cubed is equal to 0. I can factor out 1x from both of these. So therefore x could be 0. Or if I solve for y in this part, 2y minus x squared could be equal to 0, which would mean move the x squared to the opposite side and divide by 2. Y is equal to x squared divided by 2. So either of these could be true in order to make the denominator equal to 0. We do know that x cannot equal 0 for our original problem, because if I plug in x equals 0 into our original problem, I'll get 0y squared minus 0y equals 6, which is 0 equals 6, which is not true. Therefore, there's no point on the original curve that would make our slope undefined in this way if x is 0. which means we'll have to use this y equals x squared over 2 in order to make it work. So if y is x squared over 2, I can go back to my original problem again, plug that in and solve for our point. So anytime I see a y, I'm just going to replace it with x squared over 2, and then we'll solve for x. Okay, so here's a y. So this will be x times, instead of y, x squared over 2 squared, minus x cubed, here's another y, times x squared over 2 equals 6. Okay, multiply all that out. If I square this, this is x squared squared is x to the 4th times x is x to the 5th. My 2 on bottom squared is 4. Minus my x cubed times x squared is x to the 5th over 2. I do have the right powers. I don't have a common denominator though, so I'm going to multiply both of these sides by 2 to get a common denominator, and we can subtract straight across. So I've got x to the 5th minus 2x to the 5th is negative x to the 5th over 4 equals 6. So I'm going to multiply both sides by 4. It gives me 24 divided by the negative is negative 24, and then take the 5th root of both sides to get my x value. Therefore, x is the 5th root of negative 24. They only asked for the x coordinate, so at that point, I'm done. Any questions on what we did here? Okay, hi Kelly. I'm gonna take some extra time afterwards and we'll go back over the stuff that you missed. That way you won't miss anything, so we're just finishing up the first topic.
Okay.
All right. So that's it for tangent lines, which brings us to our next point. If a tangent line, I'm cutting this off a little bit, so let me change that really quick. Just can't change that. Okay, so we said a tangent line is a line that only touches our function at one point. Therefore, the slope of our tangent line is our derivative at that point. A normal line is a line that is perpendicular to that tangent line. Which does mean that in order to get a perpendicular slope to our slope of our tangent line, I would have to take the opposite sign reciprocal of the slope of the tangent line. Therefore, I could write a general form for the slope of a normal line as negative 1 over the derivative at our x value, since the derivative at our x value is the slope of the tangent line. And then if I want to write this equation of the normal line in point slope form, I would have my change in y, so that's y minus b, equals my slope times change in x, which is x minus a. So if I go back to our example here, our function is x cubed, and I want to know what the normal line would be when x is 1. So first I'm going to find our point. If x equals 1, then my y value is also 1. And then I'm going to find the slope of my normal line. The slope of my normal line is negative 1 over the derivative at our point. So first I'm going to find the derivative. The derivative of our function is 3x squared. So that means the normal slope would be negative 1 over f prime x, which would be negative 1 over 3x squared. Okay, if I plug in our x value is 1 right now, then I would get negative 1 over 3 times 1 squared, or negative 1/3 is the slope of my tangent line. Okay, then I can plug it in the same way that we did last time. I'm going to rewrite that negative sign because it looks like part of my fraction. Negative 1/3, there we go. So If I want to rewrite my equation of the normal line, this would be y minus my y value, which was 1, is equal to our slope of negative 1/3 times x minus our x value, which is also 1. Give us the slope of the line that is normal to f of x when x is 1. Slope of the line normal to Okay, we've got almost everybody back. There we go. Okay, so I could say the slope of our line that is normal to x cubed at x equals 1 would be y minus 1 is equal to our slope, which is the opposite reciprocal of our derivative, times x minus 1 in point slope form. If I wanted the slope of the tangent line instead, then we can use the original derivative, which would be 3x squared when x is 1 is 3. So that would be y minus 1 equals 3 times x minus 1. For Kelly, just lost Niall. Okay, for Kelly, this is change in y equals slope times change in x for point slope form. Okay, Kyle, I see you. What's up?
Mr. Brandon, I don't think your screen is shared.
Oh, okay. Thank you. Okay, can you see now?
Yes.
Awesome. Okay, so one more time then. Our slope of our line normal to x cubed at x equals 1 would be our change in y, so that's y minus 1, is equal to our slope, which is the opposite reciprocal of our derivative if we want the line normal to the curve. So if our derivative is 3, then our opposite reciprocal would be negative 1/3, is multiplied by our change in x, which is x minus 1. If I wanted our line tangent to the curve, I would use my original derivative. My original derivative was 3 for our slope. Everything else is the same. This is still a change in y and the change in x, where x and y values are 1, 1. Any questions on what we did for the normal line? Okay. And for most of your applications outside of electricity and magnetism, your normal line is not going to be as important as your tangent line. There are, especially when you start talking about magnets applications later on, where forces that are going to be created by your so by solenoids, by wrapped coils, are going to act perpendicular to your wire. But outside of that, we don't use normal lines a lot. Outside of pure calculus or electrostatics that I can think of. However, you're still going to see a fair amount of multiple choice questions asking about it because they need to verify that you know normal is perpendicular and it's only one step away from all of your tangent line stuff that they also need to verify. So it's like getting multiple concepts in one question if they ask for a normal line instead of a tangent line. Okay, so I'm going to try a couple of these. So once again, top of the order, back to Andrew. If I want to find the line that is normal to this function, what's my first step?
I'll derive the
Okay, we're gonna-
equation of y.
Derive this, go ahead and derive it for me.
3x minus 8x.
And-
3x squared minus 8x.
Okay, 3x squared minus 8x. I'm going to jump down to Eric. What do I need to plug in?
3.
Okay, I'm going to plug in 3 for my x value. So if I plug in 3 right now, what will happen?
27 minus 24, so 3.
Okay, so my original derivative is 3. Over to Kelly. Kelly, if our derivative is 3, so this is the slope of the tangent line, what will the slope of the normal line be?
-1/3.
Perfect. The opposite reciprocal, so the slope of the normal line is equal to -1 over the derivative of our function at that x value, which in our case is -1/3. I'm going to rewrite this. This is in the same notation. So I'm deriving not a function of x, but a function of y. Okay. So then I need the equation of the normal line next. So I'm going to jump over to Kyle. I've got a point and a slope. So how can I write my equation of the normal line?
Y plus 3 is equal to -1/3 times x minus 3.
Awesome. And they did ask us to write this in slope-intercept form, not point-slope form. So I'm going to jump to Niall to finish us off. Okay, what do I need to do first? Our goal is to get this into slope-intercept form. Right now we're in point-slope form. So what do I need to do to change this into slope-intercept form?
Oh. Slope-intercept. We need to take away 3
Okay, I need to take away
from both sides.
okay. And I also need to distribute that -1/3. So can you go ahead and distribute that -1/3 and then we'll take away that 3?
Oh, okay. So it's going to be y equals to -1/3x plus it's going to be -2.
Okay, I'm going to write that out, but this is plus, I've got the -1/3 times the -3, so that's +1 minus the 3 from the other side. Is perfect. Awesome. Okay, one more. I'm going to go in reverse order this time, so I don't hit the same people for the same questions. So Niall, back to you again. If I want to find the line that is normal to this, what do I need to do? Or what's our first step?
Wait, we're still at question 5, right?
Actually, we just finished 5, so we're going to question 6.
Oh, okay.
I'm looking for the equation of a line that is normal to this function at the given point. What would my first step be?
So if we drive y is going to be x plus 3 minus 2.
Okay, if I'm going to derive this,
Wait.
two different ways we could derive this. So you can either use quotient rule, or you can rewrite this into y equals 2 times x plus 3 to the negative first power, and then derive it using chain rule. Do you want to derive using quotient rule or chain rule?
I think chain rule will be easier.
Okay, so let's go ahead and use the chain rule. What happens if I derive this y right now?
Is it going to be x plus 3 to negative 1 times?
Okay, so I've got 2, you've got negative 1 that you were multiplying times x plus 3 raised to what power?
Oh, negative 2.
Negative 2. Okay, and then with chain rule, I would multiply by the derivative of the inside, which is 1 for us. Okay, so I'm going to multiply all of this out and we'll rewrite this. So let's finish this off and then I'll pass it to the next person. How do I simplify?
Negative 2 over x plus 3 squared.
Perfect. Okay, over to Kyle next. What do I need to plug in?
2.
Okay, I'm going to plug in the 2 since we don't have any y values. So this is negative 2 over 5 squared. Okay, so now I've got a point and I've got a slope. However, this is the original derivative. I'm going to skip Kelly since she had this question last time. And Eric, how do I get the slope of the normal line?
Negative 1 over y x derived to yx.
Okay, negative 1 over the derivative at our x value, so that's y prime at our x value. So for us, what is the slope of the normal line?
Negative 1 over 2. Oh no, 25 over 2.
25 over 2, perfect. I'm going to write an intermediary step there, just for notes for later. That was negative 1 divided by our slope, which was negative 2 over 25, which is the same thing as 25 halves. Okay, Kelly, back to you. I've got a slope of a normal line, I've got a slope of the original function, and I've got a point. How could I write in point slope form the equation of the normal line?
Y minus 2/5 equals 25 over 2 multiplied by x minus 2.
Awesome. And Andrew finishes off. They asked specifically for slope-intercept form. If they did not ask for slope-intercept form specifically, then I would stop at this step since this is an official equation of a line. But since they did, I need to keep going. So let's keep going and finish this off. Andrew, what do I need to do first to get this back into slope-intercept form?
I should use distributive method to simplify the right side.
Okay, so we're going to use distribution. What will happen to the right side?
Then it will become 25 over 2x minus 25.
Okay, and last step?
And I should add 2 over 5 to both sides in order to eliminate the negative 2 over 5.
Okay, so I'm going to make an intermediary step here, and we're going to make this over 5. 25 is the same thing as what over 5? Okay, I guess right.
125 over 5.
Perfect. This is 25 over 2x minus 125 over 5 plus 2/5. So what's our final answer?
And it will be y equals 25 over 2 times x minus 123 over 5.
Awesome. Okay. I think we've got normal lines down. So last thing for today. Okay, last technique is called Euler's method. Euler's method is sort of an alternative to integration. So we use this if we already know an equation for the differential equation. So that means we already know a formula for the slope. So what we're going to do is I'm going to take an estimate of a new y value given a point and a slope. So what it'll look like is this. Our new y value, so for the next point, should equal our previous y value plus whatever our change in y is from the last point. If that's true, then I could rewrite this, since we know our change in y should be our change in y over change in x times our change in x. I haven't changed anything since I could cancel my change in x's, right? So that means our new y value for our function should be our previous y value plus our change in x from one point to the next times our slope. Okay, so what we're really doing is if you don't know what the original function is, but you do know an equation for the slope at any point, and you know a start point. So I know an x and a y value for the original, and I know the slope of this equation at any point. An example in real life would be, let's say you're on a spaceship that's re-entering the atmosphere. You've got a really good equation for what your speed is right now, so you know your velocity, and you know what your position is right now in terms of x and y on a coordinate plane. What you don't know though is what your position function is, because your position function has a lot going into it. You've got air resistance, you've got different wind speeds as you come down. There's just a lot to integrate from your velocity, but you do know your velocity right now. So if you know your velocity right now for sure, and you know what your position is right now for sure, then Euler's method would be a way of estimating where you're going to end up in the future. So what we're going to do is we're going to take your position right now. So that's your previous y value. Y previous. And I'm going to add your change in x, which in this case would be a change in time for us. And then multiply by your change in position, in this case our change in our height, over our change in x, which is our change in time for us, to figure out what our new height will be after a set amount of time. will give us our new height. And if we keep doing this again and again and again, we will hopefully get a decent estimate for what our position will be in the future. And you can see it's not exact. If I was going to keep making more and more estimates with this, because we do know what our exact slope is at this point though, we'll end up carrying this tangent line to get a parallel line that we use for our next prediction. So we do get more and more wrong in our estimate as we go. However, the more points that you use for this, so the smaller your change in x, your step size is, the more accurate you will be. And with the help of a computer, we can make these incredibly small to get closer and closer and closer to the exact position. Okay, that was a lot. Does everyone understand our concept? So what we're doing with this equation? Any questions on the concept?
So is the y previous a point or a line, or is it just a point?
So this yp is our previous y values point. So this case would be y null. This value here.
Okay.
When you go to get your derivative, since you know what your equation for your velocity is right now, if you need to plug in an x or a y, you'll still be using your previous x and y since we're using the slope from that previous point.
Okay.
Okay, your step size or change in x is really up to you, unless the question says otherwise. But the smaller your change in x is, the more accurate your estimate will be. And again, with a computer, we can make these really small and do a lot of calculations quickly. Okay, here's another picture. So just showing what this looks like as we keep doing more and more estimates for predictions. So what we're doing is we're using this equation of a tangent line that we just talked about a couple slides ago. So that's taking our slope of our previous point and extending that for some amount of change in x to get an estimate of a new y value. So after one step, I've got an estimate a1 that is different from the exact value for this function. But because we know the exact slope of this function, we can use that exact slope to get a better estimate than I would have gotten if I kept using the same slope over time. So this would be the estimate if I just used the same slope. This is our new estimate if I change to be our exact slope at our x value equals x1. Okay, so as you can see, this is a little bit better than just doing one estimate from a point and a slope. If we keep changing based on what our exact slope is right now. Okay, so here's one example worked out. I'm just going to walk through this one and then we'll do another one from scratch. So our formula again is any new y value should equal our previous y value plus our change in x times our derivative. So that's our exact slope at that point. So I'm going to use step sizes of 0.2, so that means my change in x, is equal to 0.2 was given. To estimate what our y value would be when x is 1. If we know that our y value is 4 when x is 0, and our derivative is equal to y minus 2. Okay, so here's everything I was given. We know the step size, we know the derivative, and we know a point. Okay, so I'm going to take our previous point. So that's the y value at the previous point is y0 is 4. And I'm going to add our change in x, which is 0.2, times our derivative. Our derivative is y minus 2. My y value previously was 4, minus 2 is 2, so if I multiply that out, I've got 4 plus 0.2 times 2 is 4.4. So my estimate for what our y value would be when x is 0.2 is 4.4. Okay, any questions on what I did for step 1? Okay, then I'm going to do it again. So, oh, sorry, I saw Kelly pop up. Kelly, do you have a question?
No.
Nope, okay. So I'm going to do the exact same thing for step 2. Now my previous y value is what I had in the previous step. So my previous y value is now 4.4. So I'm going to plug that in. My previous y value is my y value at 0.2 is 4.4. Okay, my change in x is still 0.2, but my slope has changed because my previous y value changed. So instead of plugging in a 4 like I did last time, since that was my previous y value, I now need to plug in my y value at 0.2, which is 4.4. Okay, so now I've got 4.4 minus 2 is my estimate for my slope, my new estimate for my slope, times our change in x to give me my new estimate for my change in y, since my change in x's will cancel. So that gives me my previous y value plus a change in y should give me my new y value, or 4.88. Okay, any questions on our second step through? Okay, the method for the rest of this is the same, so it's just a lot more repetition. I'm going to take my previous y value of 4.88 and add our change in x times our slope. Our slope, again, is based on our previous y value. When I plug into this y minus 2, my previous y value is 4.88, so that's 4.88 minus 2 is 2.88. 2.88 times 0.2 is 0.576. If I add that to the 4.88, I get 5.456 when x is 0.6. I'll step again. So my previous y value of 5.456 plus our change in x of 0.2 times our derivative, which is 5.46 minus 2, that's y minus 2 for our derivative, is 3.456 times 0.2 is 0.6912. If I add that to the 5.456, I've got 6.1472 at 0.8. I do one more step. Our previous y value of 6.1472 plus our change in x, 0.2 times our slope, which is y minus 2. Our previous y value is 6.1472. Minus 2 is 4.1472 times the 0.2 is 0.82944. If I add that to the 6.1472, I've got 6.97664 for our final estimate for the y value when x is 1. Any questions on anything so far? No questions, okay. So again, what we've done is kind of amazing. We've just made an estimate for an integral without needing to integrate. So I'm going to go ahead and try another one that's slightly harder, and we'll see if we can do this together. So I've got our differential equation given, dy over dx is y squared times 2x plus 2. And I'm looking for f of x to be a particular solution to this differential equation with the initial condition f0 is -1. Okay, starting at x equals 0 with 2 steps of equal size, I want to approximate our f of 1/2. Okay, first, what was given? Starting with Andrew.
Our derivative is given.
Okay, so I have an equation for the derivative, y squared times 2x plus 2. What else?
And our previous y is given.
Okay, what was our previous y and what was our previous x?
Previous y is... previous x is 0 and previous y is -1.
Okay, we started at 0, -1. Okay, and then I need 2 steps of equal size to get from x equals 0 to x equals 1/2. So if I'm doing this in 2 steps, then what's my change in x?
0.25.
Perfect. I'm going to write that as a fraction as 1/4. I need 2 steps to get from x equals 0 to x equals 1/2. It's going to take me 2 steps, then each step is going to be 1/4 in length. 1 step, 2 steps. Okay, any questions on what was given? Okay, let's go ahead and get started. So our equation for Euler's method, my new y value should be equal to our previous y value plus our change in x times our slope, which is my change in y over change in x, but at one point, so that's my dy over dx at our previous point. Okay, next is Eric. So we go ahead and plug in what I know.
Uh, 1/4. No. What's y previous?
What was our starting y value?
-1.
-1, okay.
Oh.
So what we're really looking for here is our new y value would be our y value after one step size. If x was 0 and one step size is 1/4, then what would my new x value be?
Can you say it again?
Yep. Our original x value was 0. Our change in x is 1/4, so what should our new x value be?
1/4.
1/4. So I'm looking for my y value when x is 1/4. Okay, I've got my previous y value plus, we said our change in x was 1/4 times the derivative. Our derivative is y squared times 2x plus 2, but our x and y are given as 0 and -1, so we can plug that in. Okay, so what should I write?
1.
Okay, -1 squared is 1, good, times
1/2 plus 2.
plus 2. Okay, I'm plugging in our x values. Our x value right now is 0 from our previous x value, since this is our previous slope.
2.
Okay, so this will be 2. Okay, so I'm going to do all of this part first for my derivative. So that's 1 times 2 is 2 times the 1/4 is 1/2 plus our -1 for our previous point should give us our estimate for our y at 1/4. Okay. So I've got -1 plus 1/2 is -1/2 is our estimate for y at 1/4. Okay, any questions on our first step? Okay, I'm flashing. I've got 10 minutes before it kicks us out again, so I'm going to jump over to Kelly. Okay, I'm looking for a new y value. So after one more step, this will be my y value at what x value?
1/2.
1/2, perfect. Okay, should be equal to our previous y value,
-1/2
-1/2, plus my change in x,
plus 1/4.
1/4. Okay, times our derivative based on the previous x and y value.
7. 1/4.
Okay, you're right. So I'm going to plug that in though. So this is -1/2 squared times
2 multiplied by -1/2 plus 2.
close to times what?
1/4.
1/4. Okay, since that's based on our x value plus 2. Okay, so I just need to simplify. I'm going to jump down to Kyle.
So it's 1/2. So 1/2 is equal to -1/2 plus 1/4 times -1/2 squared, which is 1/4 times 2/4. So that's 1 times 1/2 plus 2.
Okay, you're right. What's 1/2 plus 2 though?
Oh wait, that's 5/2.
5/2, cool. I'm only doing that because I'm running out of space, but okay, so I'm going to multiply straight across. So this is 4 by 4 by 2 is 32. I've got 5 on top, so I've got negative 1/2 plus 5 over 32. Okay, get a common denominator and add those together, and we're done. So I'm going to jump to Niall and finish this off. Okay, so common denominator, negative 1/2 is the same thing as what?
Plus 18 over 32. Wait, no. 16 over 32.
16 over 32, okay, so this is negative,
So it's going to be negative 11 over 32.
perfect. Negative 11 over 32 is our estimate for our y value when x is 1/2. All right, any questions on anything from today? Okay, you guys are great. I've got a bunch of AP questions for us to solve that were attached on WeChat for homework. Again, I'm going to have office hours on Thursday at 10 p.m. if you guys want it. So you can show up with any homework questions you've got. Please try the homework beforehand, though, if you're going to do that.
Oh, yeah.
Okay.
All right. Thanks a lot for coming. I'm going to keep Kelly for a couple more minutes just to go back over the tangent line stuff, but it shouldn't take too long. And I will see you guys again on Thursday or next week.
Bye.
Bye.
Thank you.
Bye. Okay. So you've seen pretty much all of this already.
Yeah.
I've got a tendency for everyone to use slope-intercept form when I just ask to give me a line. So I want to point out that it's okay to keep any of these other forms, so either point, slope, standard, intercept, vertical, or horizontal form. You don't always need to go into slope-intercept form. Sometimes it can save you a lot of work if you're just given a derivative and a point to write in point slope form. So unless College Board asks you specifically for slope-intercept, I would pick whatever form is going to be the least amount of work to present. So if they just ask for a line. So even though it won't be saving too much time right now, later on you'll get to the point where we need every minute we can get. Okay, so for tangent lines, a tangent line is a line that touches our function at one point. So that means we can use the slope of our function at that point, which would be a derivative. And since we know what the point is, we can use point slope form to get our equation of a tangent line if we need it. So for this one, f of x equals x cubed. I can plug in 1 in order to get my y value. If I do, I also get 1. I can derive our equation to get our slope. If I do and plug in 1, I'll get 3. So my derivative when x equals 1 of x cubed is 3. Then I can plug that into our tangent line equation. Here's my derivative here. So that's my change in y equals my slope times change in x.
Okay.
All right, here's a couple examples. When looking for a tangent line equation, I need to derive my equation, plug in my x value to get my slope at that point, and then plug in my slope and my point to get my tangent line equation. Okay, any questions on any of these? Okay, I think all 4 of these first ones are fairly straightforward. Take a brief look at both of these derivatives. If I derive e to the u power, I get e to the u prime. So I derive e to the x minus 2. Then I would get e to the x minus 2 times 1. And then if I plug in 3, that would be e to the 3 minus 2 is e to the first power, which you don't have to write, so that's just e. Okay, for this one, if I derive with chain rule, I would still have to multiply by the derivative of the inside, so this is negative 1/3 times everything on the inside to the negative 2/3 times the derivative of the inside. Other than that, well, Okay, if I've got a negative exponent that I've got for my power, that means I can move it to the bottom of a fraction. So this negative 8 to the negative 2/3 power is the same thing as 1 over negative 8 to the 2/3 power. If I was doing this personally, I would do the bottom part of your fraction first, which means, to save time, I would be taking the cubed root of negative 8 first. The cubed root of negative 8 is negative 2, and then I would take that negative 2 and square it to get 4. And for me, that's easier than squaring this and then doing the cubed root because my numbers are a little bit smaller.
Okay.
Okay, other than that, same thing. So once we got our derivative, plug that into our tangent line equation. And they did ask for slope-intercept form this time, so I did have to rewrite into slope-intercept. Any questions on 3 or 4?
No.
Okay, so here's what it would look like as a free response. For this first part, they've asked us to take this implicit equation, which just means an equation that has both x and y's in it, which does mean that we're not a function anymore. It is possible to have more than one point at the same x value, like a circle. Okay, so for this equation, if I want to derive it, okay, so I got that timed out again.
Okay.
When school's in session, the school pays for an account, and then I'm not on a trial version. But as long as I'm on a trial version, I can only do 30 minutes at a time, I think.
Oh, okay.
Then it'll boot everybody, and we have to restart. So, anyways, I'm gonna derive this equation. If I do derive this part, I'll have to use product rule. Since we're deriving in terms of x, this is really dx over dx times y squared plus x times 2y dy over dx. But because this is deriving in terms of x, d over dx is 1 if you simplify, and you don't have to write it this time.
Okay.
If I was deriving in terms of another variable, you would have to write it. So for instance, if I wanted to derive this in terms of t instead of in terms of x, then every time you derive x, you would need to write dx over dt.
Okay.
Okay. So product rule here, another product rule here. So when I'm doing these, I just keep the negative as part of my my first part of that product rule. That way I don't accidentally mess up not carrying a negative for the second term. So this is, if I derive negative x cubed, I get negative 3x squared times dx over dx, which you don't have to write times the y I had for my second part. So all of this is also product rule for the second term.
Okay.
Okay, then if I derive the 6, that's a constant, so I get 0. Okay, for the next step, I'm going to move every term that does not have a dy over dx to the opposite side. So I'm going to add this negative 3x squared y to the opposite side.
Yeah.
And subtract the y squared to the opposite side. And now every term has a dy over dx in it, so I can factor that out. And if I factor out my dy over dx like I did here, then we can just divide by everything that's not dy over dx, and we'll get an answer for dy over dx.
Okay.
Alright, so that's a proof that dy over dx is what it said we should get.
Okay.
Next part, a little bit more interesting. I want to find all points on the curve whose x-coordinate is 1, and then write an equation for the tangent line at all of those points. So I'm going to plug in x equals 1 into our original equation to get my y values. So now, I can't erase because I did that last time. I'm actually plugging into this top equation because I need y values. So if I do, I've got y squared minus y minus 6 equals 0. And then we can factor and solve for y as 3 or negative 2, which gives me 2 points when x is 1. I have 1, negative 2, and 1, 3. For each of these points, we'll find a tangent line. So the derivative when x is 1 and y is negative 2 is our equation we got from part A. I'm just going to substitute x is 1 and y is negative 2 and simplify. So if I do, I get 2 for my derivative. And I can plug that into our tangent line equations. This is y minus b, so that's y minus negative 2 is y plus 2 equals our slope of 2 times x minus a is 1, so that's x minus 1.
Okay.
Alright, same thing for the other point. Subbing x is 1 and y is 3 into our equation for the derivative to get our slope. On top I've got 9 minus 9, on bottom I've got 6 minus 1, so that's 0 over 5 is 0. So my slope is 0, and if I plug that into my tangent line equation, everything on the right side cancels, so I get y equals 3.
Okay.
Okay. Last one, find the x-coordinate of each point where the tangent line is vertical. If I have a vertical line, that means I have some rise, but I have no run. So my slope, rise over run, would be rise over 0, which means the denominator for this dy over dx should be equal to 0 if I have a vertical tangent line.
Okay.
Example, if I wanted to graph this of a vertical tangent line, would be if you have a circle, at the edge of that circle, your tangent line equation would be vertical, which means your slope would be undefined.
Okay.
And it's possible to have more than one of those. Alright, so I'm going to take the slope, set the denominator equal to 0, solve for x. If I do, I've got an x in both terms that I can factor out, so I've got x times 2y minus x squared if I factor, means x could be equal to 0, or 2y minus x squared could be equal to 0. If 2y minus x squared is 0, I can move the x squared to the opposite side and divide by 2 to get y equals x squared over 2.
Okay.
Okay, but I've got a problem, because if I try to plug in x equals 0 to figure out what point on our function that would be, so I go back into our original problem and plug in x equals 0. If I do, I get 0 minus 0 is 6, which is false.
Okay.
So therefore, there is no point on our equation where our line is vertical because x is 0, because x is 0 is not on our equation.
Okay.
Okay, so for this one, there are no points, but I do still need to test y equals x squared over 2. So if I do, if y equals x squared over 2, then I can plug in into our original equation. Every time that you see a y, substitute x squared over 2, and then we'll solve for x to get our points. Okay, so if I do, I've got x squared over 2 squared is x to the 4th over 4 times x is x to the 5th over 4. X squared over 2 times x cubed is x to the 5th over 2, and that's negative from my subtraction sign. I've got x to the 5th, which are the same term, but I don't have the right denominator, so I'm going to multiply by 2 on both sides here to get a common denominator. X to the 5th minus 2x to the 5th is negative x to the 5th over 4. Multiply both sides by negative 4, I'll get negative 24, and then take the 5th root of both sides to get the 5th root of negative 24, which is not an even number, but is a point.
Okay.
They only asked for the x-coordinate of the point that's on the function. We did get a point using our function, so that point is on the equation. Any questions on anything from A, B, or C?
No.
All right, I believe that's where you came in.
Yeah.
Awesome. Okay, so thank you so much for coming. Please go ahead and give it a shot if you want to show up for office hours. It's Thursday at 10 to 11.
Okay.
And I can answer any questions from the homework that you guys have. Thank you very much.
Thank you.
Goodbye.
Bye bye.